Electron paramagnetic resonance spectroscopy. In this presentation, we shall discuss the principle of EPR spectroscopy and the phenomena hyperfine splitting and zero field splitting, which are the two important components of EPR spectroscopy. This electron paramagnetic resonance spectroscopy is also known by other names: electron spin resonance spectroscopy or electron magnetic resonance spectroscopy. This is an absorption spectroscopy, and the light radiation used for the study is microwave radiation or radio frequency radiation. The uniqueness of this EPR spectroscopy is that it is suitable only for molecules containing unpaired electrons, that is radicals. Now, principle. We know that electrons are negatively charged particles and are under constant spinning motion. So, they have a spin value of half. And the spin angular momentum quantum number ms can take the values plus half or minus half. As a result, we have two spin energy states. The energy of these two states are similar, that is, they are degenerate. But when the electron is placed in an external magnetic field, the degeneracy will be resolved. The spin energy state with the ms value minus half will get lower energy because the spin magnetic moment is aligned with the external magnetic field, moment of the external magnetic field. Whereas the spin energy state with the ms value of plus half will get higher energy because its spin magnetic moment is opposite to the magnetic moment of external magnetic field. This is pictorially represented in this plot. Now we have two energy states. One is with the ms value minus half, another one is with the ms value plus half. The energy gap between these two levels is delta E, which is equal to h nu, which is in turn equal to G beta h. Now a transition will occur from the lower energy state to the higher energy state by absorption of microwave radiation. But this transition will occur only according to the selection rule, that is delta ms is equal to plus 1 or minus 1 and delta mi must be equal to 0. So, for any transition to occur, it must follow this selection rule in EPR spectroscopy. This is called as the selection rule of EPR spectroscopy. The energy transition E delta E equal to h nu, which is equal to G beta h naught, as we have seen in the previous slide. Here h is Planck's constant, nu frequency of radiation, G is called as spectroscopic splitting factor or Landy splitting factor. For a free electron, the value of G is equal to 2.0023. H naught is field strength, beta is Bohr magneton. Bohr magneton is a parameter which expresses the magnetic field experiences by the electron. Expresses the magnetic field experienced by the electron. Here, the G value is an important parameter in EPR spectroscopy. It will carry two values, G parallel, G perpendicular. Depending upon the G value or based on the G value, the spectrum will be interpreted. Now, because of the transition, an absorption signal will be observed. Then, presentation of EPR spectrum. Generally, EPR spectra are plot of intensity and field strength. But the spectrum is submitted to the user in the form of derivative curves. These are the images of EPR spectrum. Now, this is absorption signal. This is a derivative curve of this absorption signal. So, to the user, the spectrum is presented only in this pattern. Here, only one absorption signal is present. Here, three signals, three steps are present. So, the derivative curve takes this form. Then, the phenomenon hyperfine splitting. So, before going to hyperfine splitting, let us just recollect the principle. That is, free electrons have spin value so that two spin energy states arise which are degenerate, but in the presence of external magnetic field, the degeneracy will be split. As a result, a transition will take place from a lower state to higher state by absorption of radiation, which results in the formation of an absorption signal. This is the principle. Now, we have a clear idea about the principle of EPR spectroscopy. Now, let us enter into hyperfine splitting. When the unpaired electron under steady comes nearer a nucleus of spin I, an interaction will take place between the unpaired electron spin and the nucleus spin. As a result of this interaction, the absorption signal will be split into two I plus 1 components. This type of splitting of absorption signal due to the interaction between electron spin and the nucleus spin is called as hyperfine splitting. This hyperfine splitting can be better understood by analyzing the EPR spectrum of hydrogen atom. Hydrogen atom has one proton and one electron. This electron, odd electron, has a spin value of half, and hence the electron spin quantum number ms can have values of plus half and minus half. The resulting two spin energy states are degenerate, as we have already seen in the previous slide. When this hydrogen atom is placed in an external magnetic field, the degeneracy will be resolved. Now, this electron spin interacts with the nuclear spin of hydrogen atom because hydrogen nucleus has a proton and that proton has a spin value of I, so that the hydrogen nucleus has nuclear spin quantum number mi, which has a value of half. Now, the coupling occurs between the odd electron spin and the odd proton spin. Each value of ms interacts with each of the value of mi, because mi can have values of plus half and minus half in the presence of this electron spin. So, each value of ms, that is plus half and minus half, each plus half as well as minus half interacts with each of the value of mi, that is plus half and minus half. As a result, 4 different energy levels will arise. These are the 4 different energy levels. Here, this is degenerate spin energy states, that is plus half and minus half of are present here. In the presence of magnetic field, there is splitting of the energy levels, that is ms with the plus minus half will be the lower energy level and ms with the plus half will be higher energy level. Now, this mi nucleus spin interacts with the electron spin energy level So each electron spin energy level is split into 2. This is also split into 2. So we have 4 different energy levels. Now energy of each level is given by the equation E equal to G beta H ms plus A ms Mi, where A is called as hyperfine coupling constant. It is nothing but the space between two signals. On substituting the values of ms and mi in the above equation, we will get the energy of the 4 different energy levels E1, E2, E3 and E4. Since we have 4 different energy levels, 2 transitions are possible. The 2 transitions are from E1 to E4 is one transition and from E2 to E3 is another transition. So this can be, again we shall go to the previous slide and we can explain 2 signals. Instead of getting one signal, 2 signals are observed and the space between these 2 signals is called as hyperfine coupling constant. We can analyze hyperfine splitting in EPR spectroscopy with the help of 5 rules. The first 3 rules are concerned with the proton nuclei, whereas the last 2 rules are concerned with the nuclei other than proton. The first rule, we shall summarize the 5 rules. The first rule, according to the first rule, the odd electron is delocalized over n number of equivalent protons. If it is so, then n plus 1 lines will appear in the spectrum. If the odd electron is delocalized over n number of non-equivalent protons, then a total of 2 power n lines will appear in the spectrum. According to the third rule, if the odd electron is delocalized over 2 sets of non-equivalent protons, that is n and m, with the spin values of ii and ij, the number of lines will be 2n ii plus 1 into 2m ij plus 1. It is the product of the 2 factors. Then fourth rule. If the odd electron is delocalized on a nucleus with a spin greater than half, that is, here instead of proton, if we have some other nuclei with a higher spin value, then we have to follow the formula 2ni plus 1 to get the number of lines. Then the final rule, that is the fifth rule. If the odd electron is delocalized over several non-equivalent atoms other than protons, which have a spin value greater than half, then the number of lines is the product of number expected for each atom. These are the 5 rules which will help to analyze the ESR spectrum of any odd electron species. Now, we shall explain each rule by taking a specific example. First, let us take rule 1 and let us consider methyl radical. Here the odd electron is delocalized over 3 equivalent protons. So according to first rule, the number of lines should be equal to 4 because the formula is n plus 1. Since all are equivalent protons, we can follow the formula n plus 1. So the spectrum will consist of 4 lines. Now we know that the spin value of each proton is half. Since in the methyl radical there are 3 protons, the total nuclear spin can be obtained by adding the 3 spin values, which is equal to 3 by 2, that is half plus half plus half. So the total nuclear spin is 3 by 2. Consequently, the Mi values are plus or minus 3 by 2 and plus or minus 1 by 2. Now, interaction occurs between each ms value of the odd electron, that is we have 2 ms values, and each of the above Mi values. As a result, 8 energy levels will appear, leading to 4 transitions. Consequently, 4 lines or 4 signals appear in the EPR spectrum. All the above discussed things are represented in this picture. Here, these are the 2 spin energy levels, and our Mi has 4 values. Each value interacts with this ms value, that is minus half. So 4 different energy states will appear. Similarly, here 4 different energy states appear, leading to 4 transitions. How do it is possible? Why the interaction is different? Because when the ms value is half, and if the Mi value is plus 3 by 2, the energy of the level will be very less. This is the fact for getting 4 different energy levels. That is, depending upon the magnetic moment of Ms and magnetic moment of Mi, the energy of the levels will differ. So only we are getting 4 different energy levels. Now, corresponding to these 4 transitions, we have 4 signals. So, in the EPR spectrum of methyl radical exhibits 4 signals. Then, the ratio of intensity of these 4 signals is 1:3:3:1. Now, we can analyze the reason why this is so, why this intensity ratio appears or falls like this. Here, these are the arrangement of proton spins in the 3 protons in methyl radical. We have to calculate the total nuclear spin. That is, the protons arrange themselves to get the total spin. We can arrange the protons with their spins in 4 different ways. In the first way, all the protons are spinning in clockwise direction, that is, all the arrows are facing upward. In the last way, all the protons are spinning in anti-clockwise direction, so all the arrows are facing downwards. In the second and third way, first let us see the second way. In the second way, 2 protons are under clockwise movement and 1 is under anti-clockwise movement. In this way, 3 arrangements are possible. In the third way, 2 protons are under anti-clockwise spinning moment and 1 is in clockwise spinning moment. That is, 2 are facing downwards, 1 is facing upward. This type of arrangement is also possible for in 3 ways. So, when we analyze the times, how many times these are present, how many times the arrangements are possible, fully upward is 1 time, fully downward is 1 time. In between ways are possible for 3 times. So only we are saying that the ratio is 1:3:3:1. This is the reason for getting the intensity ratio as 1:3:3:1. So, all the things explained or given in written form in this slide. Total spin value, we have to couple all the 3 protons. The arrangements, 4 different values are possible for the nuclear spin. 4 different arrangements are possible. So the ratio, intensity ratio is 1:3:3:1. So we have completed rule 1. Then rule 3. We shall take naphthalene anion radical to explain rule 3. According to rule 3, when the odd electron is delocalized over 2 different sets of protons, then the product will give the total number of lines. Here, the odd electron is delocalized over the entire naphthalene ring. Naphthalene ring contains 2 sets of protons. Each set has 4 protons. And all the protons are similar protons. All are having the same nuclear spin value. So we can apply the formula 2nLi Ii plus 1, and which is multiplied by 2nIi plus 1. Why we have used the same Ii? Because all are protons, all are having the same nuclear value. So that only we have used the symbol Ii for both sets of protons. Here n is 4 because in the first set we have 4 protons. So 2 into 4 into the spin value of proton is half plus 1, which should be multiplied by the splitting caused by another set of protons, that is 2 into 4 protons. Each proton has a spin value of half plus 1. So on multiplying these 2 measures, the result will be 25. Thus, in naphthalene anion radical, the EPR spectrum consists of 25 lines. So it is clarified. Rule 3 is clarified. Then rule 4. If the odd electron is delocalized over atoms which have nuclear spin greater than half, that is other than proton. Now let us take the case of an odd electron present on or delocalized over 2 nitrogen atoms. The nuclear spin value of nitrogen is 1. So we shall follow the formula 2Ni plus 1. So here, since 2 nitrogens are present, 2 into 2, I value is 1 into 1 plus 1. So 5 lines will be observed. Thus, the odd electron present on 2 nitrogen atoms will result in an EPR spectrum containing 5 lines. The intensity ratio as calculated for methyl radical, here also the intensity ratio can be calculated, which is 1:2:3:2:1. Then after explaining the rules with the specific examples, now we are we have a clear idea about the EPR spectrum of hydrogen radical, methyl radical, naphthalene anion radical, and nitrogen radical. Now let us discuss the EPR spectrum of bis-salicyldimine copper 2. This is an important compound in EPR spectrum. Here, the structure of bis-salicyldimine copper 2 is given here. Here, copper is a metal. This metal, this is in 2 oxidation state, that is Cu2 plus. Since this Cu2 plus has odd electrons in its d orbital. So, first, the odd electron in the d orbital interacts with the copper nucleus itself, and then it interacts with this nitrogen the set of two nitrogens, similar nitrogens, equivalent nitrogens, and then with these two protons. So, three steps of interactions are taking place here, so that this compound is considered as an important compound in EPR. First, the interaction occurs between the odd electron spin moment, magnetic moment, with the nuclear magnetic moment of copper, which is followed by the splitting due to hyperfine splitting due to the equivalent nitrogens, which is followed by the hyperfine splitting caused by these two protons, this proton and this proton. So, in this order, copper, nitrogen, proton. We shall discuss in detail. Copper has a nuclear spin value of 3/2. So, first the odd electron in copper interacts with the nuclear spin of copper, that is 3/2. As a result, the spectrum will lead to 4 groups of lines. Why we are saying groups instead of signal? Because this hyperfine splitting is followed by further splitting by nitrogen and hydrogen. 2 equivalent nitrogen atoms and 2 equivalent hydrogen atoms. So only we are saying the signal is not a single line. It is a group. It consists of 15 lines. Now, each of the 4 lines, because of the hyperfine splitting caused by nitrogen and hydrogen, will split into 15 lines. That is, nitrogen has a spin, 2 nitrogen atoms are causing the splitting. So, 2 into 2 into 1. 1 is 2 number of hydrogen, 2 already in the formula, 2 number of nitrogens. 1 is the nuclear spin of nitrogen, which should be multiplied by another set of splitting, another set of hydrogen which causes the splitting. 2 in the formula, 2 hydrogens, half is the nuclear spin of hydrogen plus 1. So, 5 into 3, 15 peaks will result. Each of the 4 lines will be split into 15 lines. But because of some overlap of peaks, each group contains only 11 peaks. 11 peaks are peaks alone are observable. Out of 15, because of overlapping between some lines, only 15 peaks appear. This is the EPR pattern of bis-salicylaldimine copper 2. This is one group of line, second group, third group, fourth group. These 4 groups arise from the coupling between odd electron spin and the nuclear spin of copper nucleus. And the internal 15 lines arise from coupling of this odd electron spin with the nuclear spin of nitrogen, 2 nitrogens and these 2 hydrogens. That's all about the EPR spectrum of bis-salicylaldimine copper 2. Then we enter into zero field splitting. This zero field splitting, the phenomenon is more concerned with the transition metal ion complexes, more related to the EPR of transition metal ion complexes. In general, when a metal ion is placed in a crystal field, that is transition metal ion, that is they are also called as D block metals. When placed in an external, in a crystal field is nothing but in the presence of a ligand. When brought near the ligand, they will lose the degeneracy of the d orbitals. That is, the set of d orbitals will be split into 2, T2g orbitals and Eg orbitals. But the spin degeneracy will remain. But When such a metal ion with more than one unpaired electron is placed in the crystal field, the spin degeneracy is also resolved by crystal field. That is, generally transition metal ions containing d electrons are placed in crystal field under the influence of crystal field. The degeneracy of d orbitals will be resolved. That is, they will split into two sets, T2g orbitals and Eg orbitals. But if the metal ion contains more than one unpaired electron, then the spin degeneracy of the d orbital electrons is also resolved by crystal field. This splitting of spin levels in the absence of magnetic field by the crystal field is called as zero field splitting. That is, here spin degeneracy is resolved only by the crystal field and we have not introduced any magnetic field, because in EPR the spin degeneracy is resolved only by the external magnetic field. But here in the case of metal ion, the crystal field itself resolved the spin degeneracy. No magnetic field is introduced. This type of degeneracy, resolving the degeneracy or splitting of degeneracy of spin levels in the absence of magnetic field, is called as zero field splitting. We shall take nickel 2 ion as an example. It has 2 unpaired electrons. So the total spin value will be 1. The ms values of electron spin angular momentum quantum number ms are +1, 0, -1. So the two possible transitions are, if we have 3 states, energy states, 2 possible transitions are 0 to +1 and -1 to 0. Since these two transitions are degenerate, that is require same energy, only one peak will be observed. But in the crystal field, the spin degeneracy, the degeneracy among these 3 values will be resolved. This is the phenomenon is represented in the diagram. Here ms is carrying 3 values. All the 3 values are degenerate. All the 3 levels are degenerate. In the presence of magnetic field, the degeneracy is resolved. Now we have no crystal field at all, only the external magnetic field. The degeneracy is resolved. As a result, we have 2 transitions. This is one transition, that is -1 to 0. And this is another transition, 0 to +1. Both are requiring same amount of energy. Since they are degenerate transitions, only one signal will appear in the spectrum. But if the ion is placed in a crystal field, the spin degeneracy is resolved in the crystal field itself. That is, with the ms value 0 is having lower energy and ms value 1 is having higher energy, and followed by the external splitting in external magnetic field. Again we have 2 transitions, but now these 2 transitions are not requiring same energy, they require different energies. So 2 signals will appear. There are 2 possible transitions, 2 signals will appear. This is called as zero field splitting. If there is no crystal field, we will get only one signal for nickel 2 ion. In the presence of crystal field, nickel 2 ion gives 2 signals. Next one is this zero field splitting and Cramer's degeneracy. That is, we are taking another ion as an example to explain zero field splitting. In this case, we are in a position to know about another concept, Cramer's degeneracy. First, let us take the ion Mn2. Manganese is in +2 oxidation state, which is d5 system. That is, it has 5 unpaired electrons in its d orbital. So, the Ms values are 5/2, plus or minus 5/2, plus or minus 3/2, and plus or minus half. And its nuclear spin is 5/2. So, the values are of a nuclear spin are 5/2, 3/2, and half. Now, this system has more than one unpaired electron. Automatically, we expect zero field splitting. Another point to be noted here is the number of unpaired electrons is an odd number. So, whereas in the case of nickel, we have seen 2 unpaired electrons, that is an even number. Here, the number of unpaired electrons is odd number. 5 unpaired electrons are present. So, in addition to zero field splitting, Cramer's degeneracy also will be observed. That is, Cramer's degeneracy means the spin degeneracy of every level is retained. That is, the spin energy levels are Ms equal to plus or minus 5/2, plus or minus 3/2, plus or minus 1/2. So, there are 6 energy levels. We expect that these 6 will be split into different energy levels. But in the presence of crystal field, the spin degeneracy remains. That is, Ms energy levels, that is spin energy levels, will split into only 3. That is plus or minus 5/2 one level, plus or minus 3/2 another level, and plus or minus 1/2 another level. The plus and minus have the same energy. They exist as degenerate. That is called as Cramer's degeneracy. That is, the plus or minus 5/2 will not split into plus 5/2 and minus 5/2. They have the same energy. In the presence of crystal field, they won't get separated. Only if we apply external magnetic field, all the 6 energy levels will be split. We get 6 energy levels. All the spin energy levels will be split from one another. We will have 6 energy states. As a result, 5 transitions are possible. These are according to the selection rule of EPR spectroscopy, that is delta Ms equal to plus or minus 1. So, minus 5/2 to minus 3/2 is 1. Minus 3/2 to minus 1/2. Again, delta Ms is 1. Minus 1/2 to plus 1/2. Again 1. In each transition, the delta Ms value is plus 1, either plus 1 or minus 1. Corresponding to these 5 transitions, 5 peaks result. Coupling occurs between electron spin moment and the nuclear spin moment of manganese 2 ion. Its nuclear spin value is 5/2. So, each of the 5 signal will be split into 6 components. This is because hyperfine splitting. Till then, we have seen about zero field splitting. Zero field splitting is concerned with the only crystal field, not magnetic field. Hyperfine splitting is concerned with the nuclear splitting in the presence of magnetic field. So, the spectral pattern of the splitting pattern of manganese 2 ion in the crystal field can be represented as shown in this diagram. This is the S6 level of our Mn2 ion, which is split into 3 in the presence of zero field, that is plus or minus 5/2, plus or minus 3/2, plus or minus 1/2. And each one is split into 2 in the presence of applied field, that is minus 5/2 plus 5/2. minus 3 by 2 plus 3 by 2, minus 1 by 2 plus 1 by 2. Consequently, we have 5 transitions. 3, 4 and 5 transitions are possible, leading to 5 signals, but each signal is split into 6 components, as we have seen in bis-salicylaldehyde copper 2, where each signal is split into 15 lines. Here each is split into 6 components because of nuclear splitting, that is hyperfine splitting. That's all about the phenomenon zero field splitting. We have also discussed the Cramer's degeneracy along with the zero field splitting. So in this presentation we have seen something about electron paramagnetic resonance spectroscopy, because this spectroscopic technique is an ocean. It may not be possible to discuss all things about the spectroscopy in a limited time. So we have discussed few things about electron paramagnetic resonance spectroscopy. Thank you so much for patient listening.